Hey everybody, welcome back. So this is the second part of section 2.7 where we learned that we can find the derivative and just leave it as a function using our new formula here. Not a plus h, but x plus h. We also learned the different notations and which ones we're seeing more and more. We practiced taking the derivative using our new notation. We talked about visually, how do you draw a derivative graph? And that was just by going point by point and imagining tangent lines, and the slope of those lines become the new y values of our derivative graph, and how it's great to start with bumps, because the bumps on the OG graph become x-intercepts on the derivative graph. So a great place to start. We looked at a couple examples, proved how that works. We tried one of our own. We talked about if you take the first derivative, you can keep going forward because that's a function. So let's take the derivative of the derivative, which we call the second derivative, which is f double prime. And then we looked at this function. We exhaustingly found the first derivative and the second derivative, and we looked at it visually. Again, the first graph original is just a polynomial cubic. The first derivative was a parabola shifted down, and the second derivative was just a straight line. But again, notice on these graphs, if I look for the bump on the first function, they do refer to an x-intercept or a slope of 0 on the first derivative. And if I go over to the other bump over here, yep, that's got a corresponding derivative of 0. And we can do the same thing with the pink graph, the first derivative. If I did the derivative of the derivative at that point, that gives me an x-intercept on the green graph. So that's going to be really useful later. Okay, let's talk theory here, guys. Are we allowed to take derivatives everywhere? Is everything differentiable? Differentiable just means, are we able to take the derivative? Well, okay, so what does that mean? If you are differentiable, that means the derivative exists. You can do it. The past few functions we've done, we've taken the derivative of it, so therefore, those functions were differentiable. So you're differentiable at a point if you can take the derivative at that point exists. How about an entire interval? Are you differentiable on an entire interval? Yes, if you can take the derivative at every number on that interval. Okay, so that's a little bit of theory. Fine, fine, fine. I just want you to know the word differentiable. That's the important takeaway from there. Here's your thought. This is a really interesting deep thought. Deep thought by Mr. Brown. If a function is differentiable, meaning you can take the derivative, then it is continuous. Okay, that's true. That is true. Let's just assume that's true because Mr. Brown says it's true. I'm wondering now, is the converse also true? Remember the converse from geometry? Meaning, if it's continuous, is the function also differentiable? Can I take the derivative everywhere? Now I think, well, sure. If he's continuous graph, yeah, I can take the derivative everywhere. But then, you know what? Let's think about our old friend, the pointy absolute value graph, right? That's our friend here. He's our V graph. And as you work left to right, you can take the derivative of all these points. The tangent would actually be the actual graph itself. But I get really nervous around here, guys, right? Because how do I take the derivative at that V? It's too sharp. I mean, here's the point. Would the tangent look like this or this or this? These are all different slopes, but they're all tangent to that graph. So corners on a graph are really weird. So if you are differentiable, this is really important. If you're differentiable, you're continuous. So I'll say if D, then C. Yes. If you're differentiable, then you have to be a continuous graph. But if you're continuous, are you always differentiable? No, not always. Sometimes, but not always. And that's really important to take away. For example, the absolute value graph. The cube root graph is almost the same too. You can be totally continuous, but that doesn't mean they're differentiable. Why? All right, these are the three big places where a derivative can fail. So memorize these. Put a star next to them, tattoo them onto your cheeks. All four of them. I'll wait for you to get that one. Okay, number one. Where is it bad? At a corner. Ooh, look at that corner right there. Look at it. Ooh, that's just a nasty corner because if you try to take, again, a tangent line there, I mean, I could do a tangent here. That's hitting the graph at one point. Sure. But isn't this one also? And this one? Like a corner can have an infinite number of tangent lines, which means you can have infinite number of slopes. So the slope isn't really defined. So corner, bad. If you have a sharp corner on a graph, you cannot take the derivative. But interesting, the function is continuous, but he's not differentiable everywhere. Well, how about just a discontinuity? You can't take the derivative at discontinuity because, well, where would you draw it? Here, I guess? Okay, well, again, it's a weird point. Is that the tangent? Is that the tangent? Is that the tangent? I don't know. So discontinuities are also not differentiable. And finally, is this weird one is a vertical tangent. If by chance you're drawing your tangent lines here, friends, tangent line, tangent line, tangent line, and you get to this spot right here where your tangent line is completely vertical. Do you remember from your old days? What's the slope of a vertical line? Horizontal line, that's always 0, right? But a vertical line, we don't know because it's undefined, right? It's a vertical slope. You end up dividing by 0, and you can't do it. So because you're dividing by 0, it's undefined. I need to know the derivative. So the derivative is undefined. So a vertical tangent is another place where, on a graph, it's not differentiable. So again, number 1, corner. Number 2, any discontinuity. And number 3, a vertical tangent. Memorize those. Those are the 3 spots where a function is not differentiable. So we're going to bring it back to physics. Let's go back to our friend velocity. When we first learned change in rate of position, we said when you change the rate of your position, that's called the velocity. But now that we know another word for the instantaneous rate of change, we can say that the derivative of position is velocity. Okay. So if you start with position and you take the derivative or the rate of change instantaneously of position, you get velocity. Well, let's keep going. If you take the derivative of the derivative, if you take the second derivative, well, the derivative of velocity. Okay, so you're saying, what's your change in rate of velocity? How fast is your velocity changing? How fast is your speed changing? We would actually call that the acceleration. So that's the order in which you go in. If the original function is position, the derivative of position is velocity. And the derivative of velocity is the acceleration. Okay? Well, how high can you go? Let's see. You can take the first derivative, call it f prime. Second derivative is f double prime. Look at that, the third derivative. Look at that. If you take the third derivative, is f triple prime. 3 tick marks. But you would think, okay, the fourth derivative is going to be 4 tick marks. No. We get too tired of drawing all those tick marks. So the fourth derivative is just f with a little 4 exponent kind of thing of x. Okay, and then after that, the derivative of that would be f5 of x. But we don't go much higher than that. But f prime, f double prime, f triple prime, and the fourth derivative. But the biggest thing here is I want you to take away the fact that if you start with position, the derivative of position is velocity. The second derivative of position is acceleration. Or the first derivative of velocity is acceleration. We can go further. Do you know what the third derivative is of position? What's the derivative of acceleration? When you're changing the rate of your acceleration, what's that called? We don't see it in calculus, though. You probably see it in physics. And it sounds mean. It's called the jerk. Which, if you think about in your car, if you hit the accelerator really fast, what's your car going to do? It's going to jerk for a second, right? Because you accelerate so quickly. So it's actually called a jerk. Position to velocity to acceleration to jerk. Okay, let's try it, guys. All right. I'm going to give you the same function that we did before because we did all the hard work and we already found f prime and f double prime, right? That was over here. F prime was, if you remember, 3x squared minus 1 from our last video. And f double prime ended up being just linear. All right, well, let's do what it's saying. It says, can you find f triple prime, which means I want to take the second derivative and find the derivative of that. Oh, and then let's do the fourth derivative. So I'm going to find the derivative of that. Okay, this is actually not too bad because there's no more cubes or squaring, so the derivative is actually pretty easy. F triple prime here, friends. Oops, one more triple. There we go. Okay, that's going to be the limit as h goes to 0. Now remember, f double prime, I'll put over here, was 6x, right? Okay, so x plus h, we get 6 times x plus h. That's f of x plus h. Look how easy that is. Minus the function that we're taking derivative of, which is over here. No parentheses really needed over h. Again, we can't plug h equals 0. I want to, but we can't, so we're going to do some algebra. This is the lim. As h goes to 0, of, oh, look how nice this is. Oh, Mr. Brown, you're the best. Oh, stop. All right. Oh, H's are looking pretty good, but the X's are gone, baby. So now we get the lim as H goes to 0 of 6H over H. Oh my gosh, look how nice that is. And we're left with the lim as H goes to 0 of just the number 6. So can we plug H equals 0? Sure. Nothing's going to happen because there's no H to plug into. So we just end up with 6. The third derivative, f triple prime, is just a number. It's just 6. So interesting. Remember how f had a degree of 3, f prime has a degree of 2 because it's x squared, f double prime has a degree of 1. We see it up here on the top of the page. And f triple prime has a degree of 0. So the degree goes down by 1. But that only happens really in polynomials. Rational expressions, trigonometry, logarithms are diff. But for normal polynomials, this happens. That's kind of cool. Okay, so f triple prime is just 6. Well, let's see. Let's actually find now, they said, let's find f4 of x. Let's find the derivative of that. Okay, ready? We're going to need some room here. But not a lot. Because this is our third derivative. How do you take the derivative of a number? I don't know. Let's see what happens. f4 of x is the lim as h goes to 0. Okay, if I want to do f of x plus h, and I plug x plus h into here, because there's no x to plug it into, I just get 6. Right? Because there's no x to substitute x plus h into, so I'm just left with 6. All right, that's f of x plus h. Let's do minus the f of x that we're taking the derivative, which is the third derivative. So minus that function over h. That is just kind of weird looking, because look at the numerator. Look what happens. Again, I can't plug in h equals 0 yet, but I get 0 over h, which is just the limit as h goes to 0 of 0. Okay, well, the h's are gone, kind of. Can I plug in 0? Sure, I get 0. So it looks like the derivative of a constant, number is always 0. And if I keep repeating and repeating and repeating, it will always equal 0 from now on. Interesting, interesting. Okay, so let's take a look here. Look at these graphs. So if this was the original f, which was cubic, this is f prime, which is quadratic, blah, blah. This is, actually, no, I'm assuming that they're wrong degrees. Let's just look at just the shapes of them, folks. Because actually, in all reality, if you sort of sneak ahead and look at A, do you notice how A is quadratic? So if we go backwards, B is cubic. And even though it looks quadratic, C is just a flattened out x to the 4th, and D is an extended x to the 5th. But the reason why I want you to look at this picture is not to think about degrees per se, but can we again look at where the bumps are of the original, and can you see the x-intercepts in its derivative graph? So right now, if I look at the black graph and I find a bump right here, do you see that the green graph has an x-intercept there? Which means it looks like the derivative of D is the C graph. Let's check and see. Is there another bump on the D graph? Oh yeah, right there. And look what the green graph has. An x-intercept, which means the derivative of D is C. Oh, cool. Let's keep going. Can you look at C and find a bump? All right, at C we have a very long bump here. But look, I do have an x-intercept on both A and B. So the derivative of C, is that B or A? I don't know yet. Let's do a little more investigating. Okay, let's look at maybe, well, if we go to B as well, B has a bump right here in the middle, and so does A and C. So at that point, instead of using bumps, we're just going to think about the tangent lines. If you look at the tangent lines of C again, as I go left to right, do you notice that my tangent lines are very, very negative? They're becoming 0, and then they go to really, really positive. Can you see a graph here, A or B, that starts really negative, becomes 0, and becomes positive? Well, look at this. These y values are really negative, become 0, and become positive. So the derivative of C is B. And similarly, if you look at B and talk about derivatives, look at the tangent lines on B. Very positive, very positive. Slowing down and becoming 0. And then going back to positive again. It's never negative. Can you find a graph on there that starts really positive, goes to 0, and ends up positive again? And that's your A graph here. Look at that. The y values are positive, goes to 0, and goes back up to positive again. So it looks like the derivative of B is A. So the use of bumps to find x-intercepts and finding derivative graphs is really helpful. But if by chance you get multiple answers, then just think of tangent lines and slopes. Great job, folks. So now all over, what you did is you found the derivative algebraically. That's great. You're able to now find the derivative visually. That's really good. And then finally, a good AP question would be, if you're given a set of 4 graphs, can you put the derivatives in order? And the derivatives in order would be the derivative of D is C, the derivative of C is B, the derivative of B is A. Or you can say it this way. You can say if D is the original function, C would be the derivative of that graph, B would be the second derivative, and finally A would be the third derivative. A good AP question, guys. All right, well done. That closes out section 2.8. You guys did a fantastic job. See you next time.